Alrighty, so today we're looking at an introduction to series. We started last time with sequences, and what we're going to do with that sequence is essentially add up every single term to create a series. So a series is just essentially a sum of a sequence. You add the first term plus the second plus the third as far as they want you to go. So for example, maybe you had some sort of sequence that went like something as easy as 1, 2, 3, 4, and so on and so forth. We get the idea. And let's say that they asked for the sum of the first three terms. S sub 3 would mean the sum of the first three, so we just add 1 plus 2 plus 3 to get 6. Or they could ask you for the sum of the first 5 terms, and then it'd be 1 plus 2 plus 3 plus 4 plus 5, and we get the idea. Now, our main focus in Calculus BC is actually going to be the sum of an infinite number of terms, where we start at 1, we add 2, we add 3, and then we continue adding up until our infinitely large term. I think if you look at this sequence that I just wrote up at the top here, that you could see that our sum will be infinitely large. The numbers are getting bigger and bigger and bigger, so we're always adding something larger, therefore it's going to add up to an infinitely large number. Our goal for the next 4, 5, maybe even 6 sections is actually to see if these series converge or diverge. And we say that a series is going to converge if when you take the infinite sum, and the infinite sum can start at any number. It's very common to see n equals 1 just because that'll represent your first term, up to something infinitely large of a sequence. And if we add all those up and it converges to an actual number, we usually use L as a number, then we say it converges. However, if when we add all of that up, it equals infinity, or it doesn't actually equal a number, then we say it diverges. So at its core, it's a fairly simple idea. However, there's so many different types of series to look at that what we're going to have to spend the next 4 or 5 sections on is a plethora of tests determining if something actually converges or diverges. So there's a large number of tests, and the unfortunate part, the part that's going to frustrate a lot of students, is most of them actually don't give you an answer. Meaning the test will let you know if the series converges to a number or diverges from any number, but it won't actually tell you if it converges, what number it converges to. So let's start with our easiest test so far. And the easiest test is called the nth term test for divergence. So it says that if you're given some sort of series, and I picked starting at n equals 1, but it really doesn't matter. N equals 1, n equals 10, n equals 50, as long as it starts at some specific number and it gets infinitely large. Then if you take the limit of the sequence that you're summing up, then if that limit is not equal to 0, then we say that the series diverges. And this should make a lot of sense, right? If you're adding up something, 1 equals to infinity, up to, I don't know, let's say something as easy as 2n. Okay? And you look at the limit of that as n approaches infinity, right? Plug infinity in, and we get a number that's infinitely large, which tells us that not the last sum, but the last term that you're adding on is still a number. And because you're going infinitely large, you're adding on, at the end of this, you're adding on a number, plus another number, plus another number. So it's continuously growing and growing and growing and growing, even up to infinity. We want to make sure that when we take our limit, maybe we'll do something like 1 over, say, n squared. Right? If you take the limit of that, then we should remember that the limit as n goes infinitely large of 1 over n squared is 0, which is super important because it means out at infinity, after we've been going forever and ever and ever, eventually we start adding 0 onto whatever our sum is, which means that that our sum has stopped growing, which is what we want. If it continues to grow, it's going to diverge. So, if our limit is not equal to 0, then it's easy enough to say that the series diverges. Unfortunately, pretty much every series we're going to look at will not have that true. Specifically, just about every series we're going to look at, when we take the limit, it's going to end up equaling 0. Just be super, super careful, because not every time you get an answer of 0, does the series converge? It has to equal 0 for it to converge, but there are many, many, many series that when you take the limit it equals 0 and they don't converge. For example, if you took a series that we aren't actually going to explore in this section, but it's a nice example. So the series from 1 to infinity of 1 over n, it actually diverges. Whereas the 1 over n squared that we looked at above converges. And we don't know why yet. We won't know why for another section or so. But this series here, which is called a harmonic series, diverges. Even though when you take the limit as n gets infinitely large of 1 over n, it does equal 0, which needs to happen for it to converge, it still doesn't mean that it actually converges. That's just one component of convergence. Most of the time when you're asked to use the nth term test for divergence, they'll say use the nth term test, you'll take the limit as n grows infinitely large and you'll find it won't equal 0. And right away you can say it diverges. Just remember that if it equals 0, it tells us absolutely nothing. All right, let's move on. There are two specific types of series we're going to look at here, and they're pretty basic ones, not super difficult. The first one's called a telescoping series. And it telescopes because think about how a telescope works, right? A multi-part telescope, it goes out and gets smaller and smaller and smaller as you unfold that telescope. Same thing here. So let's take a look at the first few terms. All right, we plug in 1 to find our first term. So we'd get 1 over 1 minus 1 over 1 plus 1. And actually, instead of 1 plus 1, we can do the math. We know that's 2. There's our first term. And then we need to add every term because of that summation. So now we plug in 2. We plug in our second. So we get 1 over 2 minus 1 over 3. And then we add our next one. We get 1 over 3 minus 1 over 4. Plus so on and so forth. So I think just by looking at this, we can see a nice little pattern. And that is we have this negative 1/2 term right here, and then we have a positive 1/2 coming right after. So we can tell that when we add those up, our negative 1/2 is going to cancel out the positive 1/2. Negative 1/3 is going to cancel out the positive 1/3, all the way on until we get infinitely large. So notice that our largest term is basically when you're plugging in infinity. In this case, we'll just keep it as n, so we actually get a number, and it would look something like this. We just have 1 over n, signifying the largest number we're plugging in, minus 1 over n plus 1. But notice that the first term in each of these gets canceled out by a previous one if there is a previous one. And this is a positive 1 over n right here, so there would be a minus 1 over n right before it. So these two would cancel each other out as well. So it tells us that the sum of this is actually simplified down to just 1 over 1, which is 1, minus 1 over n plus 1. And that's super easy. This would be for any number you wanted. So maybe we would say that this series would end at n equals 50. Well, we would just plug in our 50, and that would give us our final solution. However, this is not 50. We are instead going infinitely large. And we know we deal with infinity by thinking about a limit. So to find our final summation, our infinite sum, then we could just do something like this. We could say the sum's equal to the limit as n grows infinitely large of our series, which is 1 minus 1 over n plus 1. When we make this bottom infinitely large, 1 over an infinitely large number goes to 0. So we just find 1 minus 0, which equals 1. So therefore, not only does this series converge, it converges to 1. If you were to add up every single term, the final answer would be 1. Notice you could use that nth term test for divergence that we looked at before, and if you took the limit of this, the limit will equal 0, which tells us absolutely nothing. It tells us it could converge, it could diverge, but as soon as you recognize it as a telescoping series, my suggestion is you write out the first couple terms to make sure you have the pattern correct, and then the telescoping series is just that first term minus the very last one, and you're done. Notice though that this pattern right here is not always the same, and it really depends on what you start with here. These two fractions are going to be 1 apart every time because this is plus 1, so it's 1 larger. It could be a little bit different. We could look at something like this. A lot of times when you have a telescoping series, they'll disguise it from you just because people are mean. So we get the sum of this wonderful rational. You can factor it. And then using your partial fraction decomposition, we can break it down to here, where we find positive integer coefficients of 1/2, and I guess not necessarily positive, negative 1/2 as well. And if you factor out the 1/2 from both of those, you end up with the sum of 1 over n plus 1 minus 1 over n plus 3. And notice the denominators here are actually going to be 2 apart each time. The plus 1 and plus 3 are 2 apart. So let's see what happens if we write out the first few terms. We'll switch colors here. We would get that 1/2 that's out in front times. We plug in 1, that would give us 1/2 minus 1/4. We'll use smaller parentheses, maybe we'll change this to brackets for clarity's sake. Plus n equals 2 now. That becomes 1/3 minus 1/5. Has anything canceled out yet? I don't think so. So let's try another. Plus, now we plug in 3 and we get 1/4 minus 1/6. And now things are going to start to cancel. Notice that 1/4 and the negative 1/4 are gone. So what will the next one be to cancel? Not sure yet. Let's try. So let's now try n equals 4. I think we'd get 1/5 minus 1/8. And now we're starting to see things happening. The 1/5s are gone. Okay. Notice though that our fraction started at 1/4, started canceling at 1/4, then 1/5. So what'll be next? Well, the 1/6, and then a 1/7, which will occur over here, and then the 1/8, and so on and so forth. But nothing's going to cancel the 1/2 or 1/3. So we'll need both of those in our answer. And as we continue on, we'll notice that because the first two didn't cancel, that probably means the last two won't cancel either. Right? So we can have our little ellipses to show that we're going infinitely large. And then we can plug in the second to last term. And the second to last term, we would say 1 over n minus 1 plus 1 minus 1 over n minus 1 plus 3. And then we can plug in our very last one as well. So that would be plus 1 over n plus 1 minus 1 over n plus 3. And close those brackets. This will get canceled. The n plus 1s will cancel as well. But then we're still left with our last two terms. First two didn't cancel. That should imply the last two don't cancel. So therefore, our final sum is going to look something like this. It'll be the limit as n grows infinitely large of 1/2 times 1/2 plus 1/3, whoops-a-daisies, minus 1 over, that seems to be n plus 2, plus, scrolling, 1 over n plus 3. And notice our coefficients actually, not coefficients, our constants at the end actually match. Imagine that'll happen most times. Okay. And we can factor the 1/2 out front from the limit. And then I think we end up with something like this. 1/2 plus 1/3 minus 0 plus 0. So we really end up getting 1/2 times common denominators 3 over 6. 2 over 6 is 5 over 6. Multiplying straight across gives us 5/12. So sometimes you may have to write out a few more terms to see what happens. The nice part is your n terms, quite often if you factored everything out, the n terms go to 0. So even if you get those wrong, it's not that big of a deal. Just be super careful with your beginning terms and figure out what actually cancels and what doesn't. All right, moving on. I guess one last point. Notice that a telescoping series doesn't matter what it starts with. N equals 1, n equals 2, n equals 3. As long as you write out your first few terms, you're fine. So, last set. The second type of series we're going to look at is one that you may have seen before. It's called a geometric series. And the reason you may have seen this before is you could have A, seen finite geometric series, or B, much more likely, you've graphed equations of this form, which are actually exponential equations. Right? And exponential equations are usually in the form where we have the y-intercept, and we have our common ratio that we multiply by every time, and then we have our n power. Okay. The nice part is if you have a series that's exponential or a series that's geometric, it's very, very, very easy to see if it converges or diverges. In fact, if the absolute value of your common ratio, so it doesn't matter if it's negative or positive, when you take the absolute value, if it's greater than or equal to 1, then your geometric series is going to diverge. Essentially what's happening is you're dealing with a value, a common ratio that's too large, meaning our series, our sequence, our sums are going to get too large too quickly. So if you had a common ratio of 4, then you'd be multiplying by 4 every time. And if you multiply by 4, that's going to increase the value of your sequence larger and larger and larger, infinitely larger. However, if you have a value of r that's in between 0 and 1, which a lot of our students will say a fraction, and I'm like, well, be careful, because 3 halves is a fraction, that's 1.5, and that's greater than 1, so avoid trying to say a fraction. But if your ratio is a number between 0 and 1, every time you multiply that number by your sequence, it's going to decrease the sequence, right? Because if you multiply by 1/2, things get smaller. They get half as large over and over and over again. And there's a nice little proof in every book everywhere. It's on the internet. But it basically tells you that if you have a geometric series, then it's going to converge to the first term over 1 minus r. I think your book might actually tell you that it converges to a over 1 minus r, where a is this ratio right here. And that's okay, because most of our geometric series are in the form starting with n equals 0. But it would probably be more accurate to say it's going to converge to the first term over 1 minus r, because then you're not restricted to n equals 0 anymore. Then you can use any series notation where that's going to be n equals 2 or n equals 6 or n equals 12. And as long as you can find the first term, then you know what it converges to right away. And you're not restricted to having a geometric series that starts with n equals 0. Okay, and this is pretty much true for any series ever, and I have a note here written at the bottom. Notice that as long as r is within its specific range, it doesn't matter where the series begins for it to converge or diverge. And I have a couple examples down here, right? We have the same sequence. Remember, this is your sequence. The thing that makes it a series is that summation notation in the front. We have the same sequence, but different limits of summation. Starts at 0, starts at 2, starts at 17. Of course, we should be able to look at it and see that our r value, our common ratio, is 1/3 on each one. 1/3 is clearly between 0 and 1, so all three of these converge. It doesn't matter where it starts, it's going to converge. Whether or not you have an extra 5 or 10 or 40 or 1,000 terms doesn't make a difference in the long run, because you're getting infinitely large. The first 1,000, million, billion terms are so insignificant in an infinitely large scale that we don't care at all. We can also find to what they converge just by finding the first term. And the first term of this would be plugging in n equals 0. And here is our first term. Note that that first term would just be 2, because 1/3 of the 0th is 1. We can find the convergence of this just by plugging in 2. So we'd get 2/9 as the first term. And here we would plug in 17, and I have no idea what that is, but regardless, we would be able to find what it converges to. If it's a free response, I would just stop here and say, bam, convergence, done. All right, let's look at one maybe a little bit trickier and then call it a good day. The last one we're looking at is 3 over 2 to the nth, and right away you might go, okay, I'm not quite sure what that is. So you can always apply that nth test for divergence just because you're bored and you're trying to rack your brain for what other tests you remember. So you can say, let's at least take the limit as n goes to infinity. So you get 3 over 2 to the n, and you're like, well, you know, if you plug in an infinitely large number, then we get 3 over something that's infinitely large, which equals 0. Great, that tells us that our last term is going to be 0, but that doesn't tell us if it converges or diverges. But it doesn't diverge right away, so drat. And then maybe you get really clever. Maybe you decide that we can rewrite this sequence. Instead of 3 over 2 to the n, maybe it's 3 over 1 over 2 to the n. And then you rack your brain a little bit more and you realize, oh wait, we can actually factor out that nth power to become 1/2 to the nth. The reason we can do that is because if you distribute it back in, the top piece is completely irrelevant. 1 to the nth power is still 1, so we haven't changed anything at all. But the reason this, of course, is useful is because now we can see this series for what it truly is, and it's an infinite geometric. We note that the value of r is indeed between 0 and 1, so it's going to decrease the value of the sequence for every value of n that increases, and therefore we know it's going to converge. And this is a nice case because we know specifically it's going to converge to the first term, oops, I changed this to 1 all the way through. It's going to converge to the first term, so that just means plugging the first value of n in over 1 minus r. We might as well finish it all the way through. 1/2 to the 0th is 1, 3 times 1 is 3, over 1/2, and then we multiply by the reciprocal to get that it converges to the wonderful number of 6. So this introduction section has 3 key pieces. It gives you 2 types of series, geometric as well as telescoping. And I feel like these kind of just give you hope. You're like, these aren't too bad. We can actually find what they converge to. The sad part is these are really the last ones we're going to look at for a while where we actually have a nice number. The ones that we'll look at afterwards, we're just going to be able to tell if they converge or diverge. And then they give us the most basic of all tests. They give us that nth term test for divergence, where we do want to check that sequence and make sure that it goes to 0 eventually. If it doesn't go to 0, then our series will never converge because it's always getting larger and larger and larger as you add up the terms. Okay. So thanks for sitting in with this, and hopefully that made a little bit of sense. Feel free to email if it didn't, and I will talk to you later.